Awesome. And are we good to start, or do you want to wait up?
No, I think we're about right. Thanks. Get started.
All right. Okay. So first of all, I didn't realize I should also submit my kazoo preferences along with my bio. So unlike Phil, I do not play the kazoo, but unlike Sean, I do own a kazoo. So there's that. But today, what I want to do is, when we started planning this year's workshop, and this came up in last year's workshop as well, we were really hoping someone would give like a one-on-one level presentation on what it takes to build networking stacks, both software and hardware, for machine learning frameworks. Right. In the past, we've had talks that purely just cover nickel semantics, and we've had talks that covered what would it take for a vendor to build drivers or providers for different aspects of, say, PyTorch. But those didn't really capture like the broader sense for here's what the ecosystem looks like, and we didn't really have a survey of the different techniques people employ to parallelize some of those frameworks. So I want to do some of that for most of my talk. And then I also cover, I'll spend about the second half of my talk, 40 to 50% of the time, talking about how we look at this problem at Enfabrica and present a framework that we've built both in hardware and in software. And I'll present a single case study that is relevant to this audience to build on top of what Sujit was presenting earlier this morning, right? And I want to spend a decent amount of time covering what a neural network really means. And at the end of the slide, I want people to walk away with a couple things, not just how the system works, but also terminology, right? I think as more and more people start looking at machine learning frameworks, what might otherwise be general terms are starting to get either misinterpreted or they mean different things to different people, and it's important that we all speak the same language. So as I kind of walk through the workflow here, think of what it means for the network from a communication pattern perspective, and also what the terms mean, right? So let's take a simple example. This is the classic hello world of neural networks. And this is a simple image recognition problem. So you have an input, a set of images that someone is going to feed your system you're trying to train. And let's say it's a simple 16 by 16 grid of pixels, and it's a bunch of hand-drawn images. And the goal of this network you're trying to train is to predict what number is in that handwritten pattern, right? So in this example, we have input being a 7, and because it's a labeled set of input data we are used to train the system, we know we should expect a 7 out from the network. Initially, there's an input layer, and for the simple problem, let's assume each neuron in that input layer represents a pixel, right? So when you initialize the system, you would broadcast the how much a pixel is lighted up to each of those neurons, and they contain a value, also known as an activation, to represent what that pixel is doing. On the end, you have an output layer, and again, based on the problem you're trying to solve, this layer could look a little different. In this case, all I could have is a digit as an output. So I have 0 through 9 as the output layer neurons. And there are some intermediate layers. And again, depending on the problem you tend to train a system for, it could do different things. And it's often hard to capture what those do, right? Like it could look for certain patterns in the inputs. It could look for certain characteristics. It could learn from what happened in a previous layer or what the activations of a previous layer are. But we'll get to that in a second. So if you think of the progression of the training job itself, you start out with the inputs. Like I said, you could, for a single pass, let's say in the most rudimentary case, you take a single image, feed it to the network, and you assign, so the edges that are connecting these different layers carry a weight. And when people talk about parameters in machine learning, it's really a combination of the weights in these edges and how each of those layers activate themselves with some sort of a bias. So it's a collection of parameters that you would take from these different layers, do a matrix operation, and progress them through the network, right? So when people say 100 million parameters or 1.2 trillion parameters, that's really what they mean. They collectively refer to these weights and biases, and among other things, ignoring the simplification for a second. So you take this input vector and you take the weights, which are initially, let's say, randomly assigned, and you compute the next value for the next layer. And you keep doing that, and eventually, based on the values that are in the output layer, the system predicts what it thinks is the number. Let's say in this case, because the weights and biases were random to begin with, it spit out something totally arbitrary, like say 3, right? And we know that's wrong because we have a labeled data set. So the goal of this network is now to figure out what was wrong, compute the cost function, and you do that by saying each of those values should have been 0 and only 7 should have been 1, or what have you, right? Based on the input you're looking at. So you take that difference of how wrong the system was and you feed it back through the entire network. And the feeding back part is quite interesting for people like us who are network architects, because that's where you start looking into things like collective operations again, right? Where you have typically an all reduce in the classic model of training systems, where you would reduce the activation values from all those neurons in the final layer and you progress them back through the network. And you go back and see how much you need to slightly tune your weights and biases to figure out how to do this over and over again. And the goal is, if you do this a bunch of times with a bunch of images, you have enough of your weights and bias and parameters tuned to know that the next time you give it a system that an image that you've never seen before, it should give you the right prediction, right? And this is a super simplification. Like I'm showing the bare minimum example of how people are doing this, and this is not how you would run any realistic application today. It's a lot more complicated than that. And if you take two like examples that are in the news a lot, unless you've been living under a rock, you would have heard large language models and DLRMs, like recommendation models, being used a lot, right? And for those style of models, there's yet another type of layer called an embedding layer, and I'll mention that quite a bit in my presentation, because that's starting to put different requirements on both the memory subsystem and the networking subsystem. But think of embedding layer as really a hash table that represents a categorization or a group, right? So if you're thinking of word-based textual models, you could group, say, red, green, and blue into a color. Or if it's a recommendation engine model, you could look at things like item embeddings and user embeddings, right? Things like if I'm a bookstore, if I'm recommending books to someone, I have state or sparse state for what a user might like and sparse state for what a particular book might offer, and you try to compute the relationship between them and suggest a recommendation. And those are sparse layers, unlike what I'm showing here in this chart, and you need a lot of memory to represent them. So a lot of terms there. I want you to hold on to them as we move along through the presentation, right? So parameters, it is also important to understand how these models have been growing. In the HPC world, we refer to them differently, right? Like if we think of a weather model or a weather simulation, we would say, this is a 10-kilometer model, or we would say for an AMR style application, this is a 10 million atom model, right? So the AI and ML community has somewhat converged on thinking about the scale of these models in terms of parameters. Do I have a laser pointer? I do, yes. So one of the initial kind of multimodal large language model, GPT-2, that came from Google was around 1.2, I think it was 1.5 billion parameters. Seems like forever ago, but since then, the model landscape has come a long way, right? So the largest known model, publicly known model today, is around 1.75 trillion parameters. And the reason why I'm bringing up these numbers is, if you take a single GPU that's like a classic 80 with like 80 gigabytes of high bandwidth memory, you cannot fit a model that's larger than 1.2 billion parameters. And what do I mean by you cannot fit a model in a GPU? And then you need to understand how people parallelize these models, right? Like if your model says are growing out of a GPU. So keep that number in mind. Keep the 1.2 billion number in mind, and kind of the state of art is clearly in the order of half a trillion or more terabytes. And if folks were interested, all the chat GPTs and like similar chatbots that are making the rounds were largely trained on one of these 175 billion parameter models that are open source or close, depending on who's doing these applications. But that there are a whole bunch of open source models that have been kind of hovering at that model scale. Moving on. So I talked about parallelization strategies. Again, a lot has been changing in this landscape. The conventional way to do this used to be data parallelism, and we'll talk about that in some depth. And then as model sizes are growing, people start looking at model parallelism, and that opened up a Pandora's box with different techniques and each with their own trade-offs. So I don't think I'll have time to do justice to all of them. So I'll cover some key ones and draw connections to how that's important for someone who's writing a networking stack. Let's start with data parallelism. So data parallelism, I'm keeping the same example. I'm showing a chart on the left where you take the model and you replicate the model across different compute elements, right? So it could be GPUs, accelerators, what have you. And you would feed different inputs, different batches of inputs to these models. So each of them will independently go on and learn their own weights and biases and figure out how to predict for the problem space that they're presented, how to predict the outcome. So you're training the system independently, but after each forward pass, remember that all reduce I mentioned earlier, now it's not just within a node or within a single GPU, but it's globally across all the redundant copies of the model you're running for those different batch sizes, right? So you reduce across them globally, you sum whatever you figure out, and then each of them will go off and update their own weights and biases and go off at the next pass for the next batch, right? So you keep doing this over and over again, and the goal is at the end of it, you have a model that you've trained while parallelizing it across the different inputs you've got, right? That had its own set of challenges. There were both synchronous and asynchronous models where you would either run a central parameter server that will hand off the learned parameters to all the models, or you would do a synchronous MPI style, like all reduce after each pass and figure out your updated values that way. So the limit for this, like I was saying, is how much of a model you can fit into a single GPU, right? As soon as your model grows larger than the high bandwidth memory you've got, you can no longer do something like this, and you need to start looking at sharding and other model parallel techniques. So speaking of model parallelism, again, this is a very blasphemous oversimplification, but assume the same example again, where I have a model that's looking at images. Now, instead of splitting my input images across a bunch of GPUs, I'm going to take the model and split them across, say, layers. And again, there are different ways you could do this, but at the simplest form, you put each layer on a different GPU. And you can imagine now I'm feeding all inputs through to every GPU in a sequential manner, right? So you're feeding it through the layer pipeline across the GPUs. And then each output gets passed on to the other, and it becomes very HPC-like at that point, right? So you're now iteratively converging on a solution by the end of your application. But of course, serialization is bad, so people start pipelining through model parallel pipelines, right? So they would take the whole batch of inputs, they would form mini batches across them, and they would stage them through a pipeline of GPUs to keep all the GPUs active, but also all the layers active at the same time. And that also it a scaling limit around 8 to 16 GPUs, because now, as you can tell, your tightly coupled communication performs better when it's within a tightly knit group of GPUs or nodes, right? So the limit there, if you look at literature, like the best people could push that model was around 20 billion parameters. And then stuff I'm not going to discuss in more depth, but I can point to links if someone wants, is hybrid of both of these models and everything from splitting it north, south, east, west to splitting both the model and the data, right? Like there are various things people have tried, and every week there's a new paper on arXiv, if you've been following it, that explores different facets of model parallelism, right? And there are also framework-specific techniques. A popular one that has taken off is zero redundancy optimizer that originally came from DeepSpeed, ended up going into PyTorch, but that can push it up to 1 trillion parameters. So you're no longer restricted by the 1.2 billion number that was fitting into a GPU, right? So all that is great, but then you still hit limits if you don't have any extreme set of optimizations. You work both with the model developers and with hardware vendors to optimize a model to fit into the size of system you've scoped out for your particular problem, right? There's yet another technique that's making the rounds now, and this somewhat turns assumptions the HPC networking people have had around its head, right? And I'll tell you why in a second. But it's called mixture of experts. So again, imagine or visualize the same multi-layer neural network that I showed. But now instead of everyone looking at every piece of data and figuring out what characteristics to look for or how to inform the activations in layers downstream, you form these ensembles of experts, right? So if I could have a group of GPUs that looking for rings in my number, so I can tell if it's an 8, or if it's an image recognition problem, I could have a group of experts just looking at the foreground, a group of experts looking at just facial features, a group of experts looking at something else, right? So you form these different experts ensembles of experts who can look at specific facets of the problem you're trying to solve, And then there's a gating function or a gating layer that decides for a given input which expert should look at it, right? So if you can think about this somewhat in a logical manner, what this does is it reduces the compute requirements from your application, right? Meaning every GPU doesn't have to churn a matrix dot product multiplication operation on every single pass. So obviously reduce compute requirements, but you still have the same number of GPUs in your system that you've designed for, because your model sizes are going to not just stay the same, but could grow tenfold, because you now have to replicate parameters and make it available to all the experts. What that means is you have reduced parameter efficiency, right? So in HPC terms, for depending on how you scale, strong or weak scale, for the same amount of parameters you've got now, you're spending your cost of the entire neural network is growing, right? So the first models that attempted this were G-Shard from Google, and more recently Switch Transformer also from Google. They were able to push this up to, if I remember correctly, like 1.6 trillion parameters or so. But there's also an accuracy loss with this, with different model implementers are trying to explore. But you might hear more of this technique in both in literature and in practice, right? And we should talk about why this is important right after we discuss inference. So we've been focusing on training a lot. So everything that I've said up till now was somewhat biased towards training. But inference is where a lot of the latest action is happening, because one, people have realized not everyone has $1 million supercomputer sitting at home where they can train models for their little chatbot, right? So there are two schools of thought with large language models. Either people are doing their own close to chest implementations and they don't release a trained model, or they're open source models with a lot of community development that's happening, that people can run on different sites like Hugging Face, or download and run it on a few number of GPUs, or even one GPU if it's a smaller model. So, but where inference becomes important is this is where you take a trained model and deploy it and build an application that's useful to someone, right? Where you take a model and now you build chatbots, you build the mid journeys, you build the stable diffusions of the world, and you have strict SLAs on performance now. You no longer have a week or a month or a year to train a model. You now have someone sitting in front of a terminal expecting strict SLAs for responses, right? So it tends to be order of milliseconds and not weeks or days. And there's also a strict SLA on accuracy now, right? And this really changes some requirements for how you would build systems meant for inference. You're not building massive systems for inference anymore. That's just not what you want, right? Like your equation for how you build pipelines changes a little bit. And remember, I talked about embeddings. So in most of inference workloads like LLRM and DLRM inference, the embeddings become crucial right now, right? So you have memory requirements that are order of terabytes that are not going to fit either in your host memory or in your GPU memory. And so people have started looking at out-of-core staging techniques. And this again, in the 90s, HPC people were looking at this slightly differently for working data set. You would swap data in and out for the partial differential equation you're trying to solve, and then you would swap it out again and do it over and over again if it doesn't fit into working memory. Somewhat similar, but the state of art here has been to use NVMe devices, which is still, it's better than fetching it from disk, but it's still slower, and the memory bandwidth that it offers, it doesn't even compare, right? Yeah, out of core staging data. So inference is memory bandwidth bound. It's not flops bound, right? So that's also something to keep in mind. So a lot of the techniques I presented, I kind of told you up front that you should think about the collective patterns and the general network patterns that you see in those techniques, and I hope you've built a mental model. But if I were to kind of revisit those techniques in terms of collective communication, right? So there's an initial parameter distribution step and a batch setup based on whichever technique you're using, which involves a broadcast operation, very standard. The gradient descent operation, which is where you try to minimize the error in the network and you backward propagate the learnings, if you will. That is an all reduce. It could be with an average operation or some operation, depending on what kind of technique you're employing. Any synchronization you need is a barrier operation, a global barrier operation. We didn't really talk about this, but there's a class of techniques called fully sharded data parallel, which folks who built collective algorithms for MPI implementations know an all reduce is really nothing but a reduce, scatter, and all gather. But the way folks have applied it for FSDP is they split it out into those two steps, and they overlap that with communication, right? It's kind of like building a non-blocking collective, but you do it with blocking faces of a collective instead. And that's proven very effective for folks who are using PyTorch, who've demonstrated some pretty impressive numbers with that. And then mixture of experts, and I highlighted this when I was presenting that technique, but from a collective perspective, that boils down into two all-to-alls in the forward pass and two all-to-alls in the backward pass. And earlier in this conference, I forget whose talk it was, someone presented some numbers with collectives and said all-to-alls, no one's going to use that, or I'm not using it verbatim, but something to that effect. But it's interesting how any collective, particularly personalized collectives, we might offer or build as primitive to the ML model people, they will use it, right? And all-to-alls in particular is really putting stress on system design, and it will, rightfully so, is a tricky collective to optimize for, whether you're doing it in software or if you're offloading it, or if you're using or composing other like switch-based aggregation techniques to build it. And it's like, it's to folks who are writing machine learning models, it's yet another collective operation. So logically, it makes sense to use all-to-alls, right? So I'm sending personalized data from point A to point B across the entire fabric, so I'm going to use that operation. But what does that mean for someone who's building a network? It's completely different, right? Next slide. And what has this led to, right? And this is really just a survey of what I call the proliferation of CCLs, collective communication libraries. And there's more than what I'm listing here. Again, like with most things in machine learning, you realize after you present a slide, it's already outdated, like the same day. But what this has led to is this long list of attempts at building collective communication primitives and libraries. And I'm not advocating that for a standard here. Like anytime someone presents a list like this, they immediately say we need a standard. That is not what I'm here to say, right? I'm really saying like there are primitives that people want for these different machine learning frameworks, and organically the ecosystem has evolved to a point where every vendor, for them to move ahead with the technology they're building, has ended up building either a variant of an existing collective communication library or build something that works for either a particular compiler suite or a particular ML framework, or for whatever academic research that people are trying to explore, right? And I don't want to walk through each one of them. I'll just call out some interesting ones. So MPI was the original, in my opinion, the original collective communication library, right? So even today, it was started, the spec came about around 30 years back, but it is still, if you look at the APIs for all these implementations, it is still, MPI is still a superset purely in terms of the capabilities that it can offer as a collective primitive. And of course, we can get into performance debates, and that can go on forever. But purely as an API subset that it provides, it's still a superset. So Nickel, in some ways, was inspired by MPI, has a take of those collectives for NVIDIA's GPUs, and they use capabilities that they have in their hardware to optimize certain collectives. And again, that's what it is. Right? It is for NVIDIA GPUs. And Rickle is AMD's take on it. And you can walk down the list and you'll see it's something very similar, and it's vendor specific. There are some exceptions, like the Microsoft one is a wrapper around NVIDIA's implementation, but they study things like topology awareness with that, or how can I use a compiler-based DSL to synthesize collective optimizations. And for the MCRDL, which recently came out as a paper from I think DK Panda's group and others. So they look at mixing network backends, right? They can mix and match a CCL implementation that's not MPA and an MPA backend and see what happens. Let's see what else is. OpenXLA is another interesting one, right? So XLA is effectively think of it as a compiler for machine learning, right? It came from TensorFlow, and then it went into PyTorch, and others started adopting it, industry wide, and it turned into this consortium of a whole bunch of companies and hyperscalers that had vested interest in that project being successful, and that also has a high level abstraction for collectives, right? you can compile down from PyTorch or TensorFlow or MXNet or multiple different ML frameworks down to a common substrate that can translate into for network architects like us, collective operations for data movement. So yeah, if you are someone building collective communication libraries, I have a call to action for you in the end. So stay tuned. I also want to highlight some design challenges now, based kind of tying together what I presented as the ML framework landscape and from the collectives and the networking requirements around that. These are not all the challenges, but some of the challenges we've been thinking about both at Enfabrica and what the industry has been looking at as well. It is clear that there's plenty of flops available, and based on how these systems are being designed, more often than not, you oversubscribe flop. You have oversubscription of flops, and you underutilize them, right? Memory bandwidth and memory capacity becomes more important, and you end up scaling out your systems in a manner that you have effectively idle cores just because you needed additional memory capacity. 800 gigabit Ethernet is here. It is not coming. It is already here. But what that means for everything I've been talking about is networking bandwidth is caught up with memory bandwidth, right? An 800 gig link is effectively 2 channels of DDR5 memory, a little more than that even. And that changes perspective, right? Like anytime you're designing a system, it's not just local access are better and remote access are not anymore. It's now a question of what equidistant access do I have to different pieces of memory, and how do I form data movement pipelines around that effectively? It's network bad, local access good is no longer the mantra, right? We heard about link utilization and load balancing and congestion from the keynote. Aditya did a pretty good job of setting up that problem statement on Tuesday. But think of collectives again, right? So a lot of the collective patterns that I highlighted get you into incast situations, and incast issues mean you need better congestion management, and it's easy to build one-off protocols or one-off solutions that work for machine learning or work for a certain class of applications, but it's much harder to build something that works across the entire data center, right? So it's important as folks building networks to keep that in mind. But of course, everyone is going to say we also want faster collectives, and there is necessarily no single right answer here, right? One thing I would point out is just the algorithmic research that has gone behind collectives has been well established, and there are battle-tested algorithms out there, and people are still discovering techniques from 15, 20 years back that not just HPC but other communities have also explored. And people who I've seen papers that reinvented pair-based exchange and had an archive paper on it. So people are rediscovering some age-old techniques that have been employed for a while, and I think that there is some non-overlapping sets in the industry around these two communities, and we can help bridge that gap. And there's also a mosaic of transport design choices, right? So you heard Sujit talk about one example with RDMA and TCP. How do you do message framing? What are the ordering constraints around this? What does that mean for incast? And there's all these overlapping challenges, particularly when it comes to transport design. And there's some interesting work going on around that as well. We talked about model sizes outgrowing. We don't have to get into that again. But I do want to get into the next one. There is a clear desire to build vendor agnostic software stacks. And the Omnipath folks also mentioned this in the earlier talk, particularly when you start working with different class of accelerators and different types of accelerators from different vendors. You don't just have a separate SDK and a separate compiler suite, but you also have different ways of doing things like peer-to-peer communication, right? So it is getting both harder and somewhat easier at the same time. I say that because it's harder to fully build stacks that work with just one vendor and fully extract the potential of it, unless you know everything top to bottom, like the entire vertical stack. It's getting easier because both the Linux subsystem and particularly for this community, the RDMA subsystem has been making strides in how we can work with other peer devices. We heard some examples in this workshop. We've seen some work around DMA buff lately for the last couple of years. So there definitely is progress around this that will enable building networking stacks that can stay vendor neutral. And the case study that we did, I'll present in a bit here, also does something in a manner that has no special hooks into any particular vendor accelerator hooks or anything that's not standard. System topology is a huge topic. In some ways, it's an overloaded term, and it's becoming very important, right? So the topology, when people think of topology, again, going back to HPC as an example, there would be a topology service. So Slurm, when it's scheduling a job, would understand how to map, MPI process or PGAS process onto the cluster that it has in front of it, based on what it knows from both how the racks are laid out, how the NUMA nodes are laid out, and that's it. Really, you get an X% boost in performance, and everyone's happy. It's getting more trickier than that with technologies like CXL coming on. People starting to think about composable systems, which obviously we at Enfabrica are also thinking about. You're somewhat squashing the layers, and the boundary is not the same as what it was. And you can't just say, I'm going to have my job scheduler, or I'm going to have Nickel, or I'm going to have PyTorch think about topology and own it, right? It really is somewhat spanning all those layers, and you can't. It's not just topology in the traditional sense of topology anymore. It's what the topology of my collective algorithm is, what the topology of my memory access latencies are. So it's a multidimensional matrix, and not just here's the distance between my GPU and my NIC, or my NUMA node A and NUMA node B. It's more complicated than that, and there's a clear lack of both software work and interfaces here, and I think the folks here again can help drive the discussion forward. So if you think of how people have been trying to address these challenges today, you see one of two ways, and the most predominant one is the example on the left, where it's not even a question of Dennard's law dying or Moore's law ending. It's more, I'm going to take this unit of collection of hardware I have with a CPU and a bunch of host DDR, a GPU with high bandwidth memory, and a backend network that's RDMA capable, and I'm just going to scale that out, like tile it out. And because I need more HBM to fit these large language models or any large parameter models, I'm going to over provision my compute, so I get the memory bandwidth and memory capacity scaling that I need. And like I've said multiple times in the talk, that leaves you with underutilized and very expensive cores, right? Or the other thing you could do is, if you're exploring things like CXL memory, the one way people have been exploring this is you would take kind of a similar setup with a CPU and a GPU, and you would have your CXL memory hanging off of the CPU. But then you're again not fully realizing the potential of what those memory devices can do, because you're bottlenecked by the PCI switching between the GPU and the CXL memory. The GPU is not able to directly work with the CXL memory. So Enfabrica, we recently announced something called the Accelerated Compute Fabric. So what I'm showing here is the ACF-Switch flavor of it. It is a single chip solution. It connects all the components we've been talking about so far using standard interfaces, right? So on the network facing side, it is a multi-terabit interface that can provide multiple 800 gig interfaces using standard RDMA capabilities and APIs. On the host-facing side, again, it's multi-terabit copy engines that can connect up your accelerators, your CPUs, and your GPUs. And now what you can do is you can efficiently move pages from any destination to any destination, whether within this cluster I'm showing or outside the network to another such cluster. And the trick here is really the copy engines, which can move data effectively the same way, whether that's between a GPU and your host memory, or GPU to another GPU out through the network, or GPU to CXL memory, right? And the key part here is the software interfaces are unchanged. So you don't really have to change how, say, PyTorch works to make use of this architecture. Moving along, so one incarnation, let's say you had such a capability like the ACF-Switch, right? One incarnation of a system you might build for machine learning could look like this, right? Again, it's a slight variant of what I showed earlier, but you have ACF-Switch in the middle. You have a single CPU that's attached to the ACF, and multiple GPUs, and several banks of CXL memory. And remember, I said now the cost of moving data across them is going to be uniform because of the copy engine capabilities that we have. So where was I going with that? Yeah, so the ACF, now you have this system where you can move data for whether you're staging embeddings in your CXL memory or whether you have dense layers in your GPU memory. It's somewhat the same cost to access them while you're computing your ML activations, right? So I think I'm out of time, so I'm going to keep moving faster here. So in that system, what we want to do for this talk was just talk about a single experiment we did on such a system we built. So we built something called Boulevard. It's data plane software that can act as a nickel plugin for NVIDIA GPUs, but it can also take other personalities as we compose higher level primitives or build stacks for other accelerators. So I'm showing an example of a PyTorch stack where if you were to use like the data parallel interface, you would come in through the distributed classes, and you would typically pick one of many process group interfaces. It could be Glue, or which Meta originally developed, or MPI, or Nickel. So in this case, I'm going to show some data with the Nickel process group backend and Boulevard acting as the plugin. And for the data path, I used the exact same stack that Srijit presented earlier today. So if you missed this talk, I highly recommend watching that. It talks about how using standard IB verbs interfaces, we can leverage the best of both worlds from both TCP and a zero copy data movement mechanism through IB verbs. Just some highlights. Like I said, it's true zero copy all the way from the application down to hardware. The way it's built, it works with upstream kernel without needing any custom hooks for peer-to-peer communication through the GPU. It supports, for Nickel, it supports all types of pointers like host, CUDA, DMA buff. And it's been somewhat of a test vehicle for us to prove certain architectural concepts and primitives more than anything else, right? And before someone asks the question, the existing verbs plugin is not general enough and did not work for what we wanted to prove, but it also makes assumptions that are non-standard and require custom hooks for P2P communication that we didn't want to use. All right, so quick slide. So this is the test platform I evaluated this setup on. This is again something Srijit also used for the data in his talk, but it's an FPGA-based platform that has Gen 3 by 16 lanes. I think I'm getting kicked out. But... Okay, so I'll keep going. So I'll talk about results pretty quickly here. The first graph I have is operation time. So this is the Nickel operation time as Nickel tests would report. I'm comparing baseline TCP with Boulevard, and this is a broadcast operation across the two sets of the test machine boxes that I have and the GPUs they have on them. And as you can tell with the TCP stack, it's a little more predictable, and the Nickel data path is reacting quite well to the TCP RDMA implementation. We see something very similar with the Nickel bus bandwidth as well. This is a bandwidth curve. As we increase the Nickel message size that PyTorch or any other application would submit, wanted to see how unidirectional bandwidth scales up from a Nickel layer. And the TCP case, I wanted to show another chart. I didn't have time to put it together, but the cost of memory copies started bringing in stragglers in the processing pipeline, and that's what you see with the variance and the TCP number. But the TCP RDMA case was able to scale quite well as we improved the message sizes. Next steps, that experiment was really a thin slice of what we wanted to explore, but we wanted to compose higher level primitives on top of this, and we've been running experiments for how we can prove some of the other theories we've made to address the challenges that I brought up earlier in the talk. So stay tuned. We'll present more of that in some of the coming presentations. With that, I also had a call to action slide. I'll keep it brief. For folks who are building CCL libraries, please think about how impedance matches between what different hardware vendors are capable of with the gear they're building and what the machine learning stacks need. It is not just a question of building plugins for sense and receive and different operations, but it's a little more than that. Also, I urge people who are implementing these stacks to document your design choices, if not your designs. Right? There's a difference there, and it's important for people to understand why a certain decision was made in the way a particular stack was implemented, even if they don't really have to understand how the internals work. For the OFA community in general, I think we have the right mindshare here that we can drive a lot of these developments across the framework. So I'd love to see more of you all participate in things like, discuss.pytorch or the various discussion forums where people are starting to think more about networking than they have up until now. And it's important that we play a part in that conversation. And I was going to crack a joke about coming up with better names, but I'll skip that. If you have any questions about my talk or anything I presented, send me a note. If you have questions about anything that Enfabrica is building, or if you want to collaborate, please include hello@enfabrica.net, and we'll chat some more.
Okay, thank you. Oh, we can certainly type in questions. But at this time, that is our last presentation, and that wraps up the program for the final day of the 19th annual Open Fabrics Alliance workshop.